Okay, so good afternoon everyone. I am grateful to Amri and all the organizers for inviting me to speak here. So I am going to talk about one of the most famous problems in mathematics and number theory, the Riemann hypothesis, which somehow very mysteriously appears in unexpected places in mathematics, and it's my intention to make you understand how important and why this problem is so important. Okay. So in number theory we study numbers, and numbers can be factorized into primes. So primes can be thought of as the building blocks of all the numbers. For natural numbers we know that every number can be uniquely factorized into primes. So if I want to study primes, this is one of the functions which is an extremely important function for us called the Riemann zeta function, which is given by this series summation 1 over n to the s. This series is convergent for complex numbers lying in this half plane, real part of s greater than 1, and in this half plane it also has this Euler product or product over these primes of this 1 minus 1 over p to the s inverse, and this equality is nothing but equivalent to saying that all natural numbers can be uniquely factorized into prime numbers. Now notice that when if I take s as 1, I mean going very close to 1, then we get a divergent series, harmonic series over here. That immediately tells me that this product should be an infinite product. So it immediately gives me infinitude of primes, otherwise this would be, this goes to infinity, so this must also go to infinity. Now if this goes to infinity when s equals to 1, that also tells me that summation 1 over p, where p runs over prime numbers, should also go to infinity. This immediately tells me that there are more primes than any geometric progression on natural numbers. So just by staring at it without doing any work, we get something about the distribution of primes. But this is also a function which is defined on complex numbers, so complex plane, and it has some really nice properties. The first one is that although the series definition only works for the right half plane, real part of s greater than 1, this can be analytically continued to the whole complex plane except for a pole at s equals to 1, and after you do this continuation, there is some peculiar relation between the values that the function takes at s and 1 minus s. Let us try to look at it in a more pictorial way. So this is the complex plane, and here is the right half of the plane. Here the function is given by this series, which is also the same as this product, but that only happens in this particular half plane. But this function has a analytic continuation to the whole complex plane, and because of complex analysis this is unique, and the values it takes at s and 1 minus s are related. Now in this half plane, because it is a product, it is non-zero. So therefore we kind of understand what happens to the function in this half plane, which is left of sigma equals to 0. Mysterious region is this strip between 0 and 1. Now Riemann himself computed some of the zeros in this region, and he noticed that all the zeros seem to be lying on the half line, and then he hypothesized that all the zeros in this particular strip, there are infinitely many of them, all of them should lie on the half line. That is what we call the Riemann hypothesis. Okay, so all this is very well and good, but why is it so important, and what do Riemann hypothesis imply in general? So first is, of course, we started with zeta function because we were interested in understanding distribution of primes. So Riemann hypothesis should say, tell us something about primes. So suppose pi of x be the prime counting function which counts the number of primes up to x. Then one of the major discoveries of 19th century, towards the end of 19th century, is the prime number theorem. Again, by studying properties of zeta function, they proved that this pi of x is given by this integral, which is approximately x by log x, and this plus this error term. But if you assume Riemann hypothesis, you get something much better. This error term becomes really good. So this is one of the first applications. Now moreover, if I want to know about how far are two consecutive primes, if you look at two consecutive, how far they can be. So there is a conjecture of Legendre which says that if I look at any two consecutive squares, there has to be a prime between them. So in other words, two consecutive primes should be separated at most by square root of that number, prime number itself. Under Riemann hypothesis, Kramer in 1919 showed something which is much close to Legendre's conjecture, but not quite there. So he says the difference between consecutive primes, pk stands for the kth prime, is at most square root of pk, but up to some log pk. So this is almost there, and the actual expected thing is much smaller than this, but let's not get into that. So we got some information about gaps between primes, again under the Riemann hypothesis. But here is another very curious thing that Riemann hypothesis implies. So this is a story of prime races. So if I look at arithmetic progressions, we would expect any arithmetic progression where the first term and the common difference are co-prime should have infinitely many primes. Furthermore, it should be uniformly distributed across arithmetic progressions. What does that mean? If I start with any a and m which are co-prime, then a mod m, the set of, that's an arithmetic progression. The number of primes in this arithmetic progression will be the total number of primes up to x divided by the total number of congruence classes, which is congruence classes, which is phi of m. So in other words, let's look at an example. If I look at 1 modulo 4 and 3 modulo 4, we expect asymptotically both the classes to have exactly the same number of primes, asymptotically. But when we try to actually count the number of primes, which are 3 mod 4 and which are 1 mod 4, we notice that the number of primes in 3 mod 4 is always greater than the number of primes which is 1 mod 4. So this is what is called Chebyshev bias. And in the beginning of 20th century, under the generalized Riemann hypothesis, when I say generalized Riemann hypothesis, it means Riemann hypothesis for some other functions, not the Riemann zeta functions, but similar to Riemann zeta function, assuming that all the zeros lie on the half line. So then a generalized Riemann hypothesis, which we will call GRH from now on, implies the Chebyshev conjecture. So this is a really curious conjecture, but Riemann hypothesis helps us in proving such a thing. Okay. So now we go to another problem which is also of interest to computer scientists, which is primality testing. Given an integer n, you want to figure out whether it is a prime number or not, but in a good amount of time, in optimal time. So in this context, we kind of know the AKS Agarwal, Kayal, Saxena proved the famous theorem in 2002 that a primality testing can be done in polynomial time. However, long before that, the generalized Riemann hypothesis in fact implied that this can be done in polynomial time. So this is one of the examples where Riemann hypothesis had already implied something which was proved using, which took a long time to be proved unconditionally. Okay, now here is another problem again which has, which Riemann hypothesis has some impact, which is the famous question of Goldbach, which says that for any even number greater than 2, can be written as sum of 2 primes. Let's ask a slightly easier question, which is called odd Goldbach and is implied by the original Goldbach conjecture, which is that every odd number greater than 7 can be written as sum of 3 primes. For example, if you take 9, it is 5 plus 2 plus 2, take 11, it is 3 plus 5, and so on. Now it was shown by Hardy and Littlewood 1923 that under generalized Riemann hypothesis, this odd Goldbach is true for sufficiently large n. And after a few years, Vinogradov, using some average version of Riemann hypothesis, was able to prove this statement without using GRH. And more recently, Desouet, Effinger, Terriel, and Genoviev in 97 proved that this odd Goldbach is true for all numbers greater than 7 under GRH. And with some really groundbreaking work of 21st century, finally this odd Goldbach conjecture is settled by Harold Helfgott. Okay, so here is again another example where GRH had already told you something is true, and it took more sophisticated techniques and time to get the theorem unconditionally. And finally, we come to an application which is my favorite application of Riemann hypothesis. This is the study of unique factorization. Now, what is unique factorization? Not all rings that you see in your daily life has unique factorization. For example, 1 plus square root minus 5, 1 minus square root minus 5 is 6, which also can be written as 2 times 3, which in other words tells you that this type of a ring is, although it looks similar to integers, it doesn't have unique factorization. However, rings such as Z, Z root minus 1, Z root 2, they all have unique factorization. Now, there is a constant which is called the class number, which captures how far your ring is from having unique factorization. If class number is 1, that means it has unique factorization as for these things, and if it is greater than 1, then the larger it is, the farther you are from having unique factorization. So, in this context, Gauss made a conjecture that if d goes to negative infinity, then the class number goes to infinity. Okay, so that's the story, but where does Riemann hypothesis come in? This is one of the very curious phenomena that happens. It was proved by Gronwall in the beginning of 20th century that generalized Riemann hypothesis implies Gauss's conjecture. 20 years later, Doering and Mordell showed that if Riemann hypothesis is false for just the Riemann zeta function, then also we get Gauss's conjecture. And then soon after, it was shown by Heilbronn that if generalized Riemann hypothesis is false for any of those L functions for which we have for any of those L functions assumed in Gronwall's work, then Gauss's conjecture holds. So, in other words, Riemann hypothesis is true implies Gauss's conjecture. Riemann hypothesis is false also implies Gauss's conjecture. Therefore, Gauss's conjecture should be true. So, this is one of the really curious examples of this. And I'll end by giving some honorable mentions, which I don't have time to talk about. Chawla problem, smallest prime in arithmetic progression. Artin's primitive root conjecture, we know this is true under generalized Riemann hypothesis. Generalized Brouwer-Siegel conjecture, again true under Riemann hypothesis. Andreev conjecture, which has very recently been resolved, but some time ago we knew that it is true under Riemann hypothesis. Well, thanks a lot. Hopefully that has inspired you to study Riemann hypothesis.
Thank you, Anup, for this very nice talk. Do we have questions?
A very nice talk, thanks. Quick question about the proof of the polynomial time primality.
Yes.
So Agarwal Kyle Saxena gave an algorithm. Did the earlier person give an algorithm that works?
He gave an algorithm, but he kind of assumed that primes are, he assumed how well distributed primes are. You don't have to look for too much to find a prime. That kind of a statement will be implied by Riemann hypothesis. Practically speaking, it should work because, we would hope for Riemann hypothesis to be true. Yeah.